morning, everybody. We're going to finish up Chapter 8 today. You got back your video projects. I was pretty pleased with them overall. Kind of neat. Also, you got back your Chapter 7 inverted that I told you to self-grade. And if you see a cross out and a check mark, so if I crossed out your grade and check marked it, what that means is you went back and self-graded it really well, and I went ahead and gave you full credit. So the point of that exercise was for you to evaluate your own work before you turn it into me. Okay? You need to go through that level of evaluation of your own work before you turn it in. So I think the biggest one that people missed on was the two elimination reactions, where one gave the looked like a Zaitsev elimination, right? And the other one looked like it didn't go through that. And the reason that is that way, you had to take into account the mechanisms. One was an E1 elimination, one was an E2 elimination, and you had to look at the chairs, right? Because in an E2 elimination, you have to have the hydrogen and the leaving group how with respect to one another. Trans or anti-periplanar, right? And so you can only tell that if you look at the chair configurations. And so you had to draw those in order to understand what was going on in those eliminations. Okay, so again, it's very, very important that you build models and you look at things carefully when you're and understand the mechanisms when you're answering some of these questions. Because just looking at that, you would have predicted that the E2 elimination should have given you the most substituted alkene, just if it's flat, right? But you have to look at it in 3 dimensions. So today we're going to talk a little bit about oxidation of alkenes. We've already started talking about this a little bit. We're going to start talking a little bit about how we add things to alkynes. The good news is, with the exception of one reaction, the addition of things to alkynes, it usually just happens twice, right? An alkyne you can think of as 2 alkenes that share the same 2 carbons, right? If you want to think of it that way. And so the chemistry should be similar. The only thing that is really different is the addition of water. We'll talk a little bit about that. Okay? So we talked about last time about being able to add 2 alcohols across a carbon-carbon double bond, if you will. So basically adding hydrogen peroxide, although we don't use hydrogen peroxide for this, right? And we can use potassium permanganate to do this. And we end up with cis 1,2-cyclohexane diol. This reaction, it's not listed here, but we have to keep it cold, right? So keep that in mind. If it gets too warm, other reactions start to happen, which we'll learn about in a subsequent chapter. But potassium permanganate can do this. Potassium permanganate under basic conditions, what did you all learn the color of that solution was in general chemistry? It's kind of a deep purple color, right? And these diols, what do you think they're colored? They're clear. They're colorless, right? And so as the reaction proceeds, the solution becomes less and less purple. The reaction actually eventually goes clear if you're using a stoichiometric amount of potassium permanganate. Okay, and so you can actually follow the reaction by looking at the color changes. Now, we can also do this through this 2-step process where we're using osmium tetroxide, and we can get the same type of product, the cis diol, right? Why do we need 2 different reaction types? Why do we need 2 sets of reactions that appear to do the same thing? What do you think, Bob? Why bother having another tool in my toolbox?
Maybe one of them is a cheaper way to do it.
That would be potassium permanganate. It's the cheaper way to do it. But is potassium permanganate the most well-behaved? We got to keep it cold, right? Yeah, so it turns out that even though this is the cheaper way to do it, sometimes you get side products. And so having a reaction that's more well-behaved works in our favor. Which one of these? We said this is about, what did we say last time? $20 a mole for potassium permanganate. And this is about like 40 grand. 40-some grand a mole, right? So a lot of dollars, right? So fortunately, we have a way to make that catalytic, right? And we talked a little bit about that. Remember that the syn addition is taken into account by both reagents because of the structure of the metal oxide species. So if you look at the potassium permanganate, or the permanganate I should say, potassium beryllium involved here, the only way you can get these two oxygens to attack the double bond is if they come in from the same phase. If you build a model of this, you'll see that you can't get one oxygen to attack from one phase and the other oxygen to attack from the other. It's impossible. It just doesn't work out. You end up with the syn addition of the two and making the two carbon-oxygen bonds, and then water hydrolyzes off the metal, and you end up with a cis diol. 1,2 diols are also known as what? Glycols. That's right. So it's a glycol. The most common one that you all are aware of is either ethylene glycol or propylene glycol. Osmium tetroxide has essentially the same structure. Okay, so you would expect the same type of mechanism. You get this osmate species, which then has to be reduced off with sodium bisulfite. So this is a two-step process. So this step followed by that step, whereas this is all really in one pot. Okay, and we talked about the fact that we can make this catalytic, right? So if this is an oxidant, it must get what in the reaction? It gets reduced. That's right. So osmium 8 plus becomes osmium 6 plus. The alkene is now a reducing agent, and it becomes oxidized. So all that stuff that you learned in general chemistry. Osmium 6 is inactive, but we can use a mild oxidant which leaves an alkene alone, and that's NMO, N-methylmorpholine N oxide, which can oxidize osmium 6 back to osmium 8, and the reaction can continue again. So we can actually make this reaction catalytic in osmium. So even though I'm paying 40 grand a mole for osmium tetroxide, only need a little bit of it. I can recycle it, if you will. Okay. What's another bad thing about osmium tetroxide? What do you know about its toxicity? It's highly toxic. That's right. So you don't want to use stoichiometric amounts of it. If you were a pharmaceutical company and you wanted to use osmium tetroxide to do some chemistry, and they do, you have a huge burden of proof at the end that there is no osmium in your products, and that becomes a problem. So if you can get away with using potassium permanganate, usually they try to, but it has other issues that even though it's a lot cheaper, the chemistry is not as well behaved. Okay. Now there's another thing that we can do to alkene. So basically here we were oxidizing an alkene to a diol, right? We were breaking a weak pi bond and getting two strong sigma bonds. And that should go from left to right. Everybody agree with that? Right? Because thermodynamics are favorable for sigma bonds. But it turns out that in fact you can actually break the carbon-carbon bonds completely, both the pi and the sigma bonds, and get two new functional groups. Okay? If you use certain reagents, and we'll talk about those here in just a minute. So basically you could imagine taking a carbon-carbon double bond and chopping it in half and getting ketones and aldehydes in this case. This is the easiest reaction for you all to memorize. You simply take an axe and cut the alkene in half, and where those alkene carbons were, you just add oxygen to them. So instead of C double bond C, it's going to be C double bond O and C double bond O. Okay? The issue is that not all oxidants will do this. Okay? And it turns out that a great way to do this is through the use of ozone, through a process known as ozonolysis. Okay? What do you all know about ozone? In the sky? Just anywhere in the sky? It's in the ozone.
Thank you.
Ozone is in the ozone. The ozone layers that pretty low to the ground are pretty high. Quite high, right? Yeah. Ozone is not a stable compound down here on Earth. Down here on Earth. Okay? It is actually responsible for pollution. So a lot of ozone does get generated lower to the ground, but it doesn't last very long, and it contributes to pollution. So you cannot call up Sigma Aldrich, which is our preferred chemical supplier, and say, send me a bottle of ozone. They don't have it. It doesn't last that long. You have to generate ozone in the laboratory as you need it. And they actually make and sell what are known as ozone generators. Can anybody tell me how you might generate ozone from what you know about ozone in the atmosphere? How does ozone get generated in the atmosphere? It's cold, it's low pressure. That's true. What else is up way high?
Radiation.
Radiation. That's exactly right. So way up high, there's a lot of radiation from the sun, and it turns out you need to put a lot of energy in. Oxygen reacts with, or is excited by radiation, which ultimately forms ozone through a complicated process that I don't expect you to know. And so it turns out that we can do the same thing down here. We just have an ozone generator, which usually has an electric charge, discharge tube. We don't really use UV light, although some of them do. And you start streaming through oxygen gas, and what comes out the other end is a mixture of oxygen and ozone. And so you can do these ozonolysis reactions fairly easily. Notice it is a two-step process, okay? So you take an alkene, you're going to first treat it with ozone by bubbling ozone gas through it, which is not easy to do because it's very reactive. You got to have a special hood, and it's all kinds of stuff, okay? And then once you're confident that the alkene is completely reacted with ozone, you stop that reaction, and then you add a reducing agent, oddly enough, okay? So you're going to oxidize it, followed by reducing it. And there's two possible reducing agents. You can use zinc, metal, and water, which is nice and convenient. Or you can use dimethyl sulfide, which is a liquid, but not as convenient. Can anybody tell me why this might not be as convenient as zinc and water?
It's got sulfur.
And?
Sulfur's bad. It smells.
Oh, it smells horrible. Yeah, that stuff stinks like a skunk. I mean, really bad. And so a small bottle of this, you can actually drive out the entire floor of the chemistry building really quick with just a few drops spilled on the floor. So it turns out zinc, of course, is a solid metal, has no odor to it. Water has no odor to it. So a lot of people like to use zinc and water, but the nice convenient thing about the dimethyl sulfide is it is organic soluble, so the reaction goes a little faster. Okay, so whereas zinc, of course, is not organic soluble, so it takes a little longer for the reaction to occur. But this is usually the preferred reagent if it will work. And so notice what's happening. You simply cut the alkene in half, and these carbons are now part of, what's this molecule? It's a ketone, but what's the molecule? What's the name? It's acetone. That's right. That's the common name. It's propanone, right? And then if you'll notice the hydrogen, the carbon, and the methyl group are part of this carbonyl, and this is now an aldehyde, right? And so we have acetaldehyde, and this is the acetaldehyde that happens in your liver if you drink alcohol because it gets oxidized. Alcohol gets oxidized to acetaldehyde, which ultimately is responsible for the hangover, okay? Now, if you look at this particular molecule, we can have alkenes that are part of a ring. We can get ketones, in this case, cyclohexanone. And here we can get, what's special about this aldehyde? There's no R group, right? So what's the name of this one? My biology friends. This is what you use to preserve frogs, worms. Formaldehyde, that's right, embalming fluid, right there, right? So formaldehyde, which at room temperature is actually a gas, believe it or not. And so the solutions that you use in your biology lab are actually aqueous solutions that are this dissolved in water. So basically, this is going to be the easiest mechanism I've ever really taught you. You just find the alkene, cut it in half, put oxygens on, right? Pretty straightforward. You just need to use ozonolysis. Okay? Now, the way that the reaction actually works is a little complicated, and I don't expect you to understand all of the processes that are going on here. What I want you to understand is that the first reaction is simply an addition across a carbon-carbon double bond. That's why it's in this chapter. Okay? So if you look at this molecule, these oxygens will get added, and you end up with this 5-membered ring called malosonide. Okay? These are unstable, and they rearrange, and they're kind of weird because you're rearranging with a sigma bond. Most of everything that we talked about with rearrangements, right, has either been through the use of carbocations and pi bonds, right? And so you go from this so-called malosonide to ozonide. This is the end of what ozone does. What's happened to the oxidation state of carbon as we go from left to right? Is it increased or decreased? Am I increasing the number of bonds to electronegative atoms? Yes. So it's becoming more oxidized, right? Okay. That's what happens. So you wait until all the alkene is reacted to give you this ozonide. Okay? Once the ozonide has completely formed, you simply treat it with one of the reducing agents, and it removes one of the oxygens. See, we've got one too many oxygens. We've got to get rid of one of them, so we need to have a mild reducing agent. And so you add one of these mild reducing agents, and in fact, then you'll get your two carbonyl-containing products. Okay? How might you go into the lab and actually monitor to make sure that this reaction is complete? What techniques have you learned that you could use to do this? TLC. How would I use TLC? I'm not gonna say it's wrong, but how would you do it? What would you be looking for?
Well, you would test the starting reagents and then the product and see if it's still left.
Okay. Chances are you're not going to be able to detect the ozone because it's not very stable. But you could look for the disappearance of the alkene, right? So if you knew that the alkene that you were looking at had an RF of, let's just, for numbers say 0.5, right? And after 5 minutes of bubbling ozone through, you take a small sample and you see just a tiny dot, maybe you bubble it another 5 minutes until you see nothing left at 0.5, right? So that would be one way to do it. What other technique could we use?
IR.
We could use IR. What would we be looking for?
We start off looking for the C to C double bond, and
Which appears where?
which appears in the SP, which is
Give me the
between,
range.
for 15 to 2000.
Around 1,500 to 2,000, right? And so you might start looking for the disappearance of the alkene, right? See how that disappears over time, assuming that you're going to get the ozonide. Because where might we find the ozonide in terms of, since it's all sp3 hybridized bonds, it's got to be out in the fingerprint region, right? Footprint. I got you, right? So we would be looking for the disappearance of the alkene. Are alkene carbon-carbon double bond absorption strong in the IR or weak?
I think they're kind of
They're fairly weak. They're kind of medium-ish, right? They're not particularly strong. They're not like a carbonyl, right? So we might have some issues there. In fact, if I was doing this in the lab, I'd probably go the TLC route. But technically, both routes could work. You end up with the ozonide. Once you have that, then you reduce them and you get the carbonyls as your product. Okay? So let's look at some examples. Here we have a special alkene. This is known as limonene. Where do you think it comes from? Limes. It actually comes from a lot of different citrus fruits. Okay, so in the peel. Limonene is actually present in the peel of a lot of citrus fruits. Anybody know why it's in the peel of citrus fruits? It does smell very citrusy, but that's not why nature put it there.
maybe to protect something.
What might a fruit want to protect itself from?
Predators.
What kind of predators? What kind of insects? Fruit flies, right? Limonene turns out to be a very, very good insecticide for things like fruit flies. If you go buy some green fire ant killer, read the back of it, it'll say it contains limonene. This is considered a green insecticide. Have you ever eaten something that contains lemon zest? That is just lemon shavings, right? You're eating some limonene, okay? It's an insecticide, but it's fairly non-toxic to us humans, okay? And it turns out it's a hydrocarbon. It's got two alkenes. It's got a stereocenter. Can anybody tell me where the stereocenter is? Or chiral center?
Right there, the one that's attached to the bottom carbon.
Right here. That's it. And actually there is R-limonene and S-limonene, and they have different odors. And they do have different characteristics in terms of their how well they kill fruit flies. It's not huge, but there is a slight difference. So now, all we have to do is identify where the alkene carbons are. We see that there's an alkene here, there's an alkene here. We're going to treat this with an excess of ozone and then reduce. We're going to chop this bond in half and replace it with carbonyls. So what do I get? Out of this carbon, I'm going to get a ketone. And out of this carbon, because I have an R group and a hydrogen, I'm going to get an aldehyde. And here, because I'm cutting this in half, right, I'm going to get a ketone and formaldehyde that really isn't going to be attached anymore, right, because I've just chopped it off, right? And so we could go from this readily available alkene to this triketone, if you will, plus formaldehyde. Now, it turns out that next semester, one of the things you all are going to do is actually isolate limonene from orange peels. So
Yeah, they were doing that in lab.
You're-
I
what?
remember that. I remember Stina talking about that.
Yeah.
About the organic.
you'll be doing. I think you do it next semester at the very beginning.
Yeah, like the first one I do it.
And so you all will isolate this and you will test it to make sure that you've isolated the right thing. What kind of tests might you do to prove that you have limonene? It's a fairly low boiling liquid, so what might you do?
We do distillation.
Pardon? You could do distillation, but you're going to get such a small amount it'd be hard to do. Gas chromatography would be very good, and then in fact that's what you're going to use, is gas chromatography to show that you've actually isolated limonene from your orange peel. And if you all are lucky, you'll get to eat the orange as well. The only time we'll let you eat anything in lab. Another test that we can do is the bromine test. How would the bromine test work? So what would a dilute solution of bromine look like? What would the color of it be? It'd be kind of brown, reddish brown. What's the color of dihalides? They're colorless, right? And so what will happen is you'll actually take a little bit of your limonene and you'll add a few drops of dilute bromine solution and you'll see if the color disappears. That's usually a good test for the presence of alkenes. So the addition of halogen across these double bonds turns out to be important as well. And in fact, for those of you who are diet conscious, not like me, the bromine test actually turns out to be important in terms of the quality of the oils that you use. So if you buy extra virgin olive oil, they actually test it in the bromine test to see how much bromine it reacts with to determine whether or not it's truly virgin or not. Okay? And so addition across carbon-carbon double bonds is more useful than just for torturing you all in this particular class. It actually has practical use. Okay? Now we can do the same type of stuff to carbon-carbon triple bonds. However, we're going to get different products when we oxidize a carbon-carbon triple bond. After all, a carbon-carbon triple bond really is just two carbon atoms that have two pi bonds instead of one, right? So we can think of just about anything we can do to a carbon-carbon double bond, we should be able to do it to a carbon-carbon triple bond, and that is true. So we can cut the carbon-carbon triple bond in half, but instead of getting ketones, we get carboxylic acids. Okay, that's the big difference. You're going to, because you have that extra pi bond, you have to get more oxidation. And so ozone will add, but it adds twice, and you end up getting these products. The interesting thing is, and I'm not exactly sure why this is, I have to be honest with you here, you don't need a reducing agent to get this all the way over. Because you're going to a higher oxidation state, water works really, really well. And you can just break down that malosonide or the dimalosonide that you get just by hydrolysis of water. So you react in the presence of ozone, and then basically you take that and you just dump it over ice water and you get these carboxylic acids. And that's how you get two carboxylic acids here, because this is an internal alkyne. If you have a terminal alkyne where you have one CH bond, when you cut it, you're going to get your carboxylic acid for this piece, but this last carbon ends up being oxidized all the way to carbon dioxide and polymerization. So if we add ozone to a carbon-carbon double bond, we get what kind of functional groups? Go to a double bond. We get ketones or aldehydes, depending on what's attached, right? And triple bonds, we get carboxylic acids, right? Now, we've talked about adding all kinds of things, all kinds of things. Time to go home. We can add all types of things. How about that? To carbon-carbon triple bonds, just like we did to carbon-carbon double bonds. So you can imagine if we had a reagent, remember at the very beginning of this chapter we just used the generic reagent, we can sacrifice a weak pi bond and get two new strong sigma bonds, right? But now we still have a carbon-carbon double bond. And so it doesn't necessarily stop. It can add again, and we can get now 4 new bonds that are sigma bonds. And so the reaction should lie to the left or to the right? To the right, exactly, just like we would expect. And so basically, everything that we've talked about adding to a carbon-carbon double bond, we can do to a carbon-carbon triple bond and get exactly the same product. It just happens twice, okay? So we can get, instead of alkyl halides, we get dihalides. if we add HX across a carbon-carbon triple bond. Okay? Instead of a dihalide, we get a tetrahalide if we're adding bromine and chlorine across a carbon-carbon triple bond. Okay, so we can do a lot of those types of things fairly easily, with the exception of water. Water gives us a different product. Okay? So if we take one butane, 2 moles of HX, and here X can be chlorine, bromine, or iodine, we get hydrohalogenation, but it happens twice. What's interesting about this?
Both the halogens are on the same carbon.
Both halogens are exactly on the same carbon. We have to explain that. Okay? We have to understand why that is the case. Can anybody take a stab at it? Why should that be the case? It is Markovnikov's rule. And we're going to talk about Markovnikov's rule in relation to this. Because you might expect that the halogens might want to be on opposite carbons due to the electronegative character of the halogens. But it turns out that's not the case. We can add X2 if X is chlorine or bromine, same as if it were an alkene, and we can get halogenation where we've added 4 CX bonds to our molecule. Okay. Here's what's different. If I add water across a carbon-carbon triple bond, I do not get a diol. I get a ketone or an aldehyde, depending on what I'm dealing with. That's different, and we need to figure out why that's the case. Okay? So we'll talk about that in just a moment. Okay? So you need to know if you're going to add water across a triple bond, you're not going to get an alcohol. You're going to get a ketone or an aldehyde, depending on whether you're doing the addition of water in the presence of mercury and sulfuric acid, or whether you're doing the hydroboration oxidation sequence. So hydroboration oxidation sequence will typically give you aldehyde and for a terminal alkyne and give you a ketone for this other procedure. Okay. So let's look at why we get what we get when we add HX across a carbon-carbon triple bond. Markovnikov's rule states what?
Hydrogen goes to the one with the most hydrogens.
All right, so if I got carbon-carbon, right? Which one of these carbons has the most hydrogens? This one, right? So if the hydrogen goes here, I'm going to generate a carbocation here. Okay? So now what happens? The bromide attacks this carbocation. This, by the way, is not a highly stable carbocation at all. It's very reactive. This happens very quick. This is known as a vinyl carbocation. And this bromide will attack very, very quickly, and we end up generating now a vinyl bromide. Okay, vinyl is just the carbon-carbon double bond. Now we have excess HBr around. It reacts again. What does Markovnikov's rule state? Hydrogen goes onto the carbon with the most hydrogens, and now I generate this carbocation. But wait a second. Shouldn't this carbocation be unstable because it's an electron-deficient carbon attached to an electronegative atom? Right? Doesn't it seem like it should be more stable or less stable than this carbocation? Why not? It's more substituted.
Yes.
And what else? It is secondary, and what else?
Can it share the charge or something?
How? What's not shown on the bromine that's really there?
It's really negative. 3 loads.
There's lone pairs, and what will those lone pairs do? They'll form a pi bond there, won't they? Right? Because this has an octet or no octet? No octet, right? So we want our most stable Lewis structures to have octets, right? And so that's what happens. The bromine with its lone pair of electrons simply forms a bromonium ion. Okay, so you do get a bromonium ion, but it's not a 3-membered ring bromonium ion. It is a bromine that is doubly bound to this carbon. And so if you think about this, bromine really doesn't want to be positively charged, does it? So the next bromide comes in and simply attacks here, breaks that very weak pi bond, and you end up with the dibromide that you see. Again, we're following Markovnikov's rule, okay? So nothing new there really, other than the fact that the halogens are going to go to the same carbon. Okay. And so we don't call these vicinal dihalides, we call them general dihalides. General means sharing the same carbon. It's very hard to stop at these vinyl species. Although you can do it if you're very, very careful. And they do this all the time on an industrial scale. How many of you have heard of polyvinyl chloride?
PVC.
PVC, that's right. You've got to have vinyl chloride to do this. One way to make it is from the addition of HX to a carbon-carbon triple bond in such a way that it stops here. But under most conditions, it's hard to control, and this ends up just adding again, and you get the geminal dihalide, or the geminal dibromide in this particular case. Okay. Why might this be difficult to stop? What do we know about HCl? Solid, liquid, or gas? It is a gas. Gases are difficult to control. What do you know about HBr, pure HBr, solid, liquid, or gas? It's a gas as well. Both of them are very difficult to control. You don't do these reactions in water solution. These are gaseous reactions. And so it's very difficult to control a single equivalent of a gas in a reaction mixture, at least on a laboratory scale. Once you get chemical engineers involved, they can usually solve these types of problems. But in a laboratory scale, using regular round bottom flasks and straws and tubes and other things, it's kind of hard to control. And so you end up usually taking these all the way to the geminal dihalides, even if you try to make these. So there's some practical issues that are there. Okay. The addition of halogen, you're going to get a tetrahalide. It's pretty straightforward. First equivalent adds, you get the trans dihalide in. The second equivalent adds, and you get the tetrahalide. Okay, so we can do this with bromine or chlorine. If we try to do this with fluorine, it goes boom. If we do this with iodine, it's versatile, right? So we're really limited to chlorine and bromine here. And so we can end up with the tetrahalides pretty easily. So if you need to put a lot of halogens on a molecule, this is a great way to do it. And it turns out that molecules with lots of halogens, at least historically, have been things like pesticides. And so using this type of chemistry has been very useful in that type of industry as well. Okay? The mechanism is a little strange, but not too terribly surprising, really. If you think about it, we add one of the halogens to one of the pi bonds, just like we did before, the same mechanism as with the alkene. You end up with this chloronium ion here. It's bridged. What's strange about it is that this is a carbon-carbon double bond still, and you have a nucleophile coming in and attacking this carbon, breaking that weak, extremely weak sigma bond. Do you suspect that this sigma bond is stronger or weaker than the one before?
The one
When we did the alkenes, when we just did alkenes.
I'll say weaker.
You're going to say weaker?
You said extremely, extremely weak.
It is extremely weak.
Is it because the pi bond is there?
Well, the pi bond puts a little more
Does it
strain.
have to do with like the geometry?
Yeah, you got to take into account geometry.
Because it's a double bond, so it has like 120,
Wants to be 120, right?
but it's at like 60.
And so that's way off, right? Yeah. So attack here happens. You open that up. Now we have the trans dihalide, but now we have a carbon-carbon double bond again, which simply reacts with another molecule of halogen. You now end up with this chloronium species. You have the second equivalent of chloride come in and open that up, and you end up with the tetrahalide. So again, nothing particularly new there. Okay? So let's look at some examples of things.
You just be strong.
Dr. Rangachari's in here after this, so I better leave it up a little bit.
Yeah, yeah. You have to jump once.
I'd like you there.
Let's look at the addition of water across an alkyne first. And let's try to understand that mechanism, because it's the one that we do not get the expected product. We don't get a diol. Okay, so if we take a carbon-carbon triple bond, and let's just put a methyl group. So if I have sulfuric acid and water, usually you add a little mercury to this just to make it go a little faster, but it's really not the oxymercuration, demercuration sequence, so don't get confused by that. What's going to be the first step? How do I think of sulfuric acid and water? I'm going to think of it as H plus, right? Yeah, so I've got H plus and HSO4 minus, right? It's completely dissociated because it's a strong acid, right? And so the pi bond is going to react with H plus. Markovnikov's rule tells me what?
Hydrogen goes to the carbon with the
That's right. So I'm going to draw the arrow. Right? Don't forget the geometry. Now what happens?
Now we have that HSO4 minus to go in there.
Do we? Is that going to be my nucleophile?
No, water.
No water, yes.
Water's going to be the
Yeah,
nucleophile,
yeah,
right?
yeah.
So water is going to attack. Right, and end up with a protonated alcohol, if you will. Which what happens now?
More water because it
Takes the rest.
Because it's acid catalyzed, right? So I gotta get my acid back.
yes.
And it looks like I've made an alcohol, correct? You all agree with that? Carbon bound to an OH, right? But is it a typical alcohol? It has a double bond. All the alcohols that we've been talking about so far have been bound to an sp3 hybridized carbon, right? This is an alcohol bound to an alkene, okay? This is known as an enol. Because you might think, well, why don't we just add another molecule of water, right, and end up with a geminal diol? I could draw arrows to take care of that. But it turns out that this intermediate called an enol, do you think they're stable? They are not stable. And they do a process called tautomerization. They tautomerize, which is basically a fancy word for rearrange. Explain what just happened there. I did make a ketone. Are there any new atoms in the product that weren't in the enol? No. So these are equilibrating species of one another, and the equilibrium lies to the right. Okay?
That's why I got it.
So how do I draw the mechanism for this happening? Well, I'm going to draw the hydrogen over here. Where does this hydrogen end up going?
Down going to the right.
To this carbon. What happens to this pi bond?
It moves to the, yeah, just like your air pi bond.
That line in the arrow.
Or we could push it the other way, right? I could push
It's that way.
this like that. Which way is correct? Think the first one is correct? So let me erase this. Let's evaluate it. If I look at this oxygen-hydrogen bond, where do the electrons really reside most of the time? On the oxygen or the hydrogen? Kind of on the oxygen. But this is saying that they're leaving with the hydrogen, right?
So we need to draw the
Need to go the other way. But it gets me both the same places, but it's not taking everything into account. Right? So this comes down to make the pi bond, and the pi bond gets that acidic proton. Okay? And this is called tautomerization. And the reason that you don't get an alcohol or a diol out of this hydration reaction is because once you form this, it tautomerizes, and now you have a ketone, which doesn't react with the water and sulfuric acid any further. Okay? And so you no longer have that carbon-carbon double bond. Okay? So that's the big thing that we need to keep in mind, is that we're going to have this polymerization process. Now, if we use the second reaction, hydroboration, oxidation, I end up with what? I end up with an aldehyde. How do I add OH or water across the carbon-carbon bond here? It's anti-Markovnikov, right? So I end up with that's right. I end up with the OH on the least substituted carbon. That's still an enol. It's still going to rearrange, but when it rearranges, it's going to rearrange to the aldehyde, not the ketone. Okay? So that's the difference there. Has everybody got it? Just a second. Does anybody have their syllabus with them? Wednesday, don't we have a problem session?
What was most days the problems?
Be the night.
We have a catch-up and reaction review.
Okay.
We have a problem on the 16th.
Hmm?
The problem session is the 16th.
But we have a catch-up and review, reaction review on Wednesday. Yes.
2 days from now.
Yeah, Wednesday.
Yeah, that's just-
So the reactions review, when we come in, because I've covered everything that I need to cover for chapter 8, okay? When we come in, I'm going to have some problems. We're all going to work on the board. We're all going to get up and do some work, so be prepared for that, okay? Now, one person's going to go to the board for basically each row, but everybody in the row is going to help, okay? And we've got a whole series of reactions now in our bucket, so to speak, and we need to get better at picking out which reactions we need for various reactions. So we'll have more problems, kind of like problem, what was it, 5 on the inverted lecture? So a product, work your way back to a needed starting material. That's what we're going to do on Wednesday. So make sure you're read up. And on your way out, you can just leave chapter 8 inverted lecture up there.
Pages just scribbled with chemistry stuff.